Hello friends, welcome back to Quantum Quandary. In this video I'm going to explain what groups are. So I'm going to start with the definition and then perhaps we can interpret it a little bit. So the definition, a group G is a set with an operation. Let's call the operation circle. The circle takes G to G. It takes G cross G to G, such that G prime is taken to G circle G prime, such that. So, first of all, we want for all G prime and G, and G second in G, that G circle G prime circle G second is G circle G prime circle G second, i.e. it's associative. The second property, there exists for all G in G, there exists an identity element E in G, such that for all G in G, we have that G, let's say it like this, EG is G. And the third, this I specifically write as acting from the left, because acting from the right can be derived. And for all G in G, there exists a G inverse in G, such that G inverse G is E. Okay, so from these three properties, kind of trivial properties, follows a beautiful theory. And the reason why is, well, at least qualitatively, these sets that are groups, they are self-contained with respect to this operation there. You could say invariant under it, and this causes a lot of symmetries to be able to arise from these models. So let's give an example. An example would be, let's say, Z3. So I take the numbers 0, 1, 2, and I add them to each other such that I take the mod 3 value, the remainder of the division by 3. So, of course, mod 3, 0 is 0, mod 3, 1 is 1, mod 3, 2 is 2, or I could write it like this, 0, mod 3. Okay, and then if I change here to 4, right, so mod 3, 4 would be mod 3, 3 plus mod 3, 1, and this is 0, so that's 1. So basically periodicity. So we have the line of positive integers, and we identify 0 with 3, and so on. So it makes a sort of loop like this. This would be 0, 1, 2. And then 3 is equal to 0, 4 is equal to 1, and so on. Okay, so in this group, in this set, if you consider the pair Z3 in addition, you get a group. You get a group such that 0 plus 1 is 1, it's in Z3. 0 plus 2 is 2, it's in Z3. 1 plus 2, well, 1 plus 1 is 2. 1 plus 2 is 3, which is 0, which is in Z3. You see what I mean, mod 3, right? And so on. There is an inverse. So for all G in Z3, there exists an inverse. So yeah, you basically you need to check the 3 properties to show that it's a group. So maybe I should have gone in order, but it's such a trivial example that I feel as though it's better to go by feeling than by order. So if I take the element 1, its inverse is 2 because 1 plus 2 is 0. 0 is going to be the identity element because anything plus 0 is the thing. So okay, yeah, let's take it methodically. So property 1 would be associativity, right? Of course, addition is associative, so addition is associative. You don't need to check. So you have this property. The second property, the identity, well, 0 is the identity because n plus 0 is n for all n in Z3, definitely true for all n in any vector space, of course, but... And the third one, yeah, just G inverse is basically 3 minus n, right? So it's 3 minus G, or n inverse is 3 minus n. So because 3 minus G plus G is 3 is 0. Or I guess, yeah, well, the reason I write 3 minus G, this minus is just the algebraic minus, right? Arithmetical minus. It's not defined in the context of the group. It's just, I mean, so 0 inverse is 0, 1 inverse is 2, 2 inverse is 1, and so on. Okay, and now I just want to add, so this was an example of a group, but actually making a group is interestingly constrained. So if I tell you how many elements your group has, you don't have much choice. Suppose that the dimension of G, which I'll just denote by this, the size, right? Not dimension, the order of G, the size of the set is 1. So you just have one element. Well, then, of course, G is just the identity, because you need to have the identity in G. The identity is its own inverse, everything is fine, it's associative. Okay, so only one group of order 1. Suppose G is 2. Okay, I can say that G is E and A. The identity needs to exist in the group. And we're going to get the following. So because A times A, I'm going to just omit the action symbol and look at it as multiplication. So A times A, it could either be E or A, right? Because it needs to be in the group. So if it is A, if A times A is A, then A equals E, because A is the element which, when you multiply A with, you get itself. So it's E. So that's a contradiction, because then the group size would be 1, it wouldn't be 2. So you know that A times A is E, therefore A is A inverse. This would be called the cyclic group of order 2, and it would be isomorphic to Z2, which is 0, 1, with addition as the operation, right? Because 0 plus 1 is 1, 1 plus 1 is 2, which is 0, because it's mod 2, it's just this 0, 1. Okay, even further, so if G is of size 3, G is E, A, B, 3 distinct elements, the identity is there, and same thing, like you could play around. In fact, I encourage you to try doing this, and you'll get that AB has to be E, meaning B is A inverse. And so yeah, basically you just have E, A inverse, or you could say that it's EA, A squared, because you're going to get that A A is A inverse as well. I encourage you to try. So then this basically means that it's isomorphic to Z3. Okay, and the last example that I want to do, well, not example, we're going up. So where it gets interesting, I suppose, is dimension 4, because here you do have a choice. So when G is 4, G is E, A, B, C. So as you can see, we keep getting the cyclic groups, so I could suppose that G could be Z4, right? In which case you would have E, A squared, A cubed. Let's call it G1, G2. G1 is E, A squared, A cubed. Because, why do I write it like this? Because it's like A times A is A squared, A times A cubed is E, for example, and so on. So it's going modulus 4. So and so the other one is another choice. The way you can see this is you can draw something that's called a Kaley graph. So basically you're looking at it like this, and you're wondering, I wish I could use 2 fingers. So you're acting with this column on this row. E on E gives E, E on A gives A, E on B gives B, E on C gives C. This is why I write this column basically representing itself. Okay, and then if I act with A on A, I'll get A squared, which is just A times A. Well, let's write it A. A on B gives A B. You get it, right? But from here, there is actually a theorem, I think Lagrange's theorem, that tells you that these cannot repeat per line or per column. Maybe I can prove that in the next video. But so from this, you're going to get that one of the options is this behavior, but another one of the options is going to be, let's see. So you could have that each element is its own inverse here, something like this. And if each element is its own inverse, then you can kind of see that these 3 elements have to be taking each other to one another, to the third one. So for example, B on A should give you C. C on A should give you B, C on B should give you A. You see what I mean? Like they're cycling through each other. So A on B gives you C. It's a commutative group because A on B gives you the same as B on A. So B on C should give you A, and you end up with something like this. You can check that it works fine. So each element is its own inverse, and it's a group of size 4. Okay, but you can see how these 3 kind of fun but seemingly coming out of nowhere properties that we give in the definition of a group force us to choose very particular types of sets. Okay, well, that's my introduction to groups. Hopefully you guys liked the video. See you next time. Bye.